I just want to start this video with a quick disclaimer. In this video, I will teach you how to do stoichiometric conversion calculations, but I will not cover the topic of stoichiometry and chemical equations itself. I have a complete video over that on my channel. If you're looking for help on that, you can go to that video. With that out of the way, let's get started. Defined in the Oxford Dictionary as a small, burrowing insectivorous mammal with dark velvety fur, a long muzzle, and very small eyes, when you hear the word mole, you are probably thinking of this animal. In chemistry, of course, a mole is not some glorified rat. Rather, it is the base unit in the system of units for amount of a substance. Similar to, say, a dozen or a pair, a mole just describes how much of something there is. In chemistry, you will use the mole for conversions between the amount of stuff, a process known as stoichiometric conversions. And that's pretty much it. The mole itself will make a lot more sense when we use it in stoichiometric conversions. Let me start by writing down some common conversion amounts you can do with the mole. We're going to start with one of the most useful conversions and one that you will 100% be using in your chemistry class, and that is Avogadro's number. That is this guy over here. This is Avogadro. Pretty much, his number states that 1 mole of a substance contains 6.022 times 10 to the 23rd molecules. 1 mole of water, for instance, would contain 6.022 times 10 to the 23rd molecules of water. 1 mole of oxygen would contain 6.022 times 10 to the 23rd oxygen molecules. Avogadro's work is also linked to the idea of molar volume. Molar volume pretty much states that 1 mole of a substance will have 22.4 liters of that substance, as long as we are at standard temperature and pressure. Although this will always be the case unless it is otherwise specified. Finally, the last very common and useful conversion you will be using in your class is the molar mass. The molar mass pretty much states if you go down to the periodic table and you look at an element, you see where it has its atomic mass. 1 mole of an element is equal to its atomic mass. So for example, 1 mole of oxygen would be equal to 16 grams of oxygen. 1 mole of hydrogen would equal 1 gram of hydrogen. So that's the first part of the video done. Now let's move on to stoichiometric calculations. What are stoichiometric calculations? The way that I always understood stoichiometric calculations was we're taking an amount of something in a certain unit and we're just putting it into another unit. For some calculations, this is really easy, and you can just do them in your head. For instance, how many pounds is in a dozen pounds? It's 12 pounds. How many liters is in 1,000 milliliters? It's 1 liter. These conversions are very, very simple. Obviously, we wouldn't have to do any work for them. But for other calculations, such as how many molecules of hydrogen are in 20 grams of water, that is a lot more difficult. I have no clue how you would do that in your head. But the basic principle is the same. We can't do grams to molecules. There is no magical ratio for that. But there are smaller ratios. We can do grams to moles, and we can then go from moles to molecules. And so by adding additional steps in the middle, we can still solve these conversion problems. I think that's enough yapping for now. Let me just show you some examples, and then these problems will make a lot of sense. They're really quite intuitive, I promise. I don't think this will be something you're struggling with in your chemistry class. So let's say I have 1 mole of water, and I now want to know how many molecules of water I have. I know this is simple, you could probably do it in your head, but I want to show you how to set up a stoichiometric chart. The way that I set up the charts is you turn this first one into a fraction, and then you multiply it by another fraction. Because remember, a ratio is just a glorified fraction. 1 to 2 is the same as saying 1/2. So we do know that 1 mole is equal to 6.022 times 10 to the 23rd particles. That's Avogadro's number. So where do we put the mole, where do we put the particle in this fraction? Does the mole go on the top or on the bottom? Well, we start with moles, but we want to end up with particles. So we need this mole, which we can think of as a variable, to cancel. And the only way to cancel variables and fractions is to have one variable on the top and that same variable on the bottom. So we would take 1 mole H2O, and we know that this 1 mole of H2O is equal to 6.022 times 10 to the 23rd molecules. This is one more thing I'm going to comment on. you'll see that mole is technically spelled out MOLE, but you can abbreviate it to just MOL. You cannot abbreviate molecules. I know your chemistry teachers are going to call you out on this, and you might even get frustrated with them. You might think they're crazy. You cannot abbreviate molecules. It's not molec, it's molecules. You just got to write it like that. I'm sorry. But so now, continuing on, as you can see here, we have a mole on the top and a mole on the bottom. So we can cancel out these variables. And if we cancel out variables, what's the one thing we're left with? It's just molecules. So now we can multiply our tops by one another, and we will end up with 6.022 times 10 to the 23rd molecules of water. Make sure that you're always writing your unit. Your unit is molecules, your compound is water. Make sure you're writing all this down. This would be your final answer. Pretty simple, right? As you can see, once you've done one of these problems, you kind of get the basic gist. But let's do another one just to make sure it's getting through. This time, let's do 20 grams of water, and let's find how many molecules of hydrogen. So again, let's start by turning this into a fraction and finding what we need to multiply it by. Well, I know that I can't do grams directly to molecules, but I can do grams to moles. How do I do grams to moles? Well, that's just the molar mass. Remember that 1 mole of a substance equals the atomic mass of that substance on the periodic table. Well, water isn't on the periodic table, but oxygen is, and hydrogen is. The way that I could find the molar mass of water is just by taking the molar mass of oxygen and adding it to the molar mass of 2 hydrogen atoms. What's the molar mass of oxygen? It's 16. What's the molar mass of hydrogen? It's 1. And I have 2 hydrogen atoms, so I'll add 1 twice. And that will give me an answer of 18 grams. So I know that for every mole of water, I have 18 grams of water. Now, where do I put my grams? Where do I put my moles? Well, I want my grams to cancel out because I want to end up with molecules. So I'm going to put grams on the bottom. I'll put 18 grams down here of water, and then at the top, I'll put 1 mole of water, because again, that's my ratio. The next thing I want to do is convert this moles into moles of hydrogen. Now, you may not know how to do this yet, and that's okay. I have a full video on stoichiometry and stoichiometric ratios on my channel, which I implore you to check out if you'd be stumped on this step. But the way you got to look at it, every mole of water has 2 moles of hydrogen and 1 mole of oxygen. How do I know this? Well, I mean, just look at it. This oxygen has an implied subscript of 1, and this hydrogen has a subscript of 2. So 2 moles of hydrogen and 1 mole of oxygen in every mole of water. So if every 1 mole of H2O has 2 moles of hydrogen, well, then I can just put that ratio on my chart. I have mole up here, and I want to cancel out mole. So I would put 1 mole. What should I do? Water or hydrogen? Well, I should do water, because I'm trying to turn it into hydrogen. Whichever value you're putting on the numerator of the fraction is what you're going to be turning into. So down here, I would write 1 mole of water, and up here, I would write 2 moles of hydrogen. Now we've just got one final step. We want to turn this into molecules. What is Avogadro's number? Well, for every 1 mole of hydrogen, I get 6.022 times 10 to the 23rd molecules hydrogen. And now all I have to do is cancel and then multiply it out. This gram will cancel with this gram, this mole will cancel with this mole will cancel with this mole, and you can also cancel the compounds themselves if you'd like to, water, 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 hydrogen, hydrogen. But that'd only be necessary if you think you've made some mistakes along the way or you're not feeling completely stable in your answer. And so when you multiply out the top and divide it by the bottom, put that all in your calculator, you get a final answer of 1.338 times 10 to the 24th molecules hydrogen when adjusted for significant figures. I hope that calculation made sense to you, but if it didn't, just rewatch this part of the video. If you're still not getting it, just take a break. Let's finish this video off with one final equation. If I have 40 grams of carbon dioxide, how many grams of carbon do I have? Well, to solve this, let's first set up our first fraction, and then let's think. I need to go from grams to moles of carbon dioxide first. To go from grams to moles, I need to find the molar mass of carbon dioxide. The molar mass of carbon dioxide is just the molar mass of oxygen, times 2 because I have 2 oxygen atoms, plus the molar mass of carbon. Adding these numbers up, I get a final answer of 44. And so for every 44 grams of carbon dioxide, I will have 1 mole of carbon dioxide. Now, let's change from moles of carbon dioxide to moles of carbon. 1 mole of carbon dioxide has 1 mole of carbon. How do I know that? Well, just look at the subscripts. There's a implied 1 below the carbon, and there's a 2 below the oxygen. Now, I just need to go from moles of carbon to grams of carbon. To do this, I just need the molar ratio. For every 1 mole of carbon, I get 12 grams of carbon, because that's its molar mass on the periodic table. And so I can take this, cancel the grams, cancel the grams, cancel the mole, cancel the mole, cancel the mole, cancel the mole. You get a final answer, 11 grams of carbon when written with the appropriate number of significant figures. Thank you so much for watching this video. I hope it has given you a better understanding of the mole, of how stoichiometric calculations function, and of how we can solve chemistry problems using this knowledge. If you're struggling to understand this, try rewatching parts of the video. If you're still not getting it, just take a break and come back later. Thank you.